Hello friends, we are going to see certain basic properties of real numbers in this video. Let's first define the binary operation. If you have a non-empty set A, then an operation star on your set A is called binary if for every element small a and small b inside your set capital A, the new element obtained by performing this operation star denoted by A star b is also a member of A. For example, you consider your operation star as addition and your set A as set of integers. We know that addition of two integers is again an integer. Therefore, we can say operation addition is an binary operation on our set of integers. Similarly, if you take your operation as multiplication, then and your set A as your set of integers only, then we know that multiplication of two integer is again an integer. Therefore, we can say multiplication is also an binary operation on our set of integers. But if you take division and your set A as set of integer only, we know that division of two integer need not be an integer. For example, you consider 1 by 2. 1 is integer, 2 is integer, but 1 by 2 is not an integer. Therefore, we can say operation division is not an binary operation on our set of integers. Similarly, if you consider your set A as set of natural numbers and you take your operation star as minus, then we know that subtraction of two natural number need not be natural. For example, you consider 1 minus 2. 1 is natural, 2 is natural, but 1 minus 2 which is equal to minus 1 is not a natural number. Therefore, minus is not a binary operation on our set of natural number. But minus is an binary operation on our set of integers because we know that subtraction of two integer is again an integer. Therefore, you can say minus is binary on set of integer, but minus is not binary on our set of natural numbers. Now let's see the algebraic properties of our set of real numbers denoted by R. On this set of real numbers R, we have two binary operations called addition and multiplication. Addition is denoted by this plus symbol and multiplication is denoted by this dot symbol. And these binary operation, addition and multiplication, satisfy certain properties which are called algebraic properties that are listed below. Let's see it one by one. First property, see I am using this notation A1, A2, A3, A4. That means these are the properties of addition, and for multiplication I am using the new notation M1 and then below M2, M3, M4. Those are the properties of multiplication. Let's see the first property with respect to the addition. It is the commutative property of addition. That means the order in which you are adding the real number is not important. That means a plus b is equal to b plus a for all a and b inside our set of real numbers R. Second property is associative property. That means if you are adding three real numbers, then if you add a and b first and add c to it, it is same as if you add b and c first and then add a to it. That means a plus b then added c to it is same as b plus c and then added a to it. Next property is existence of an additive identity. That means there exists an element in R which we denote by symbol 0 such that if any real number is added to this 0, then I will get my real number back. That means if a is any real number, then 0 plus a is equal to a and a plus 0 is equal to a. Next property is existence of an additive inverse. It states that for every element a in my R, there exists an element which we denote by minus a in R such that a plus minus a is my additive identity 0 and minus a plus a is also my additive identity 0. So these are the four properties with respect to addition. Now we will see the properties with respect to multiplication. Again, properties are almost similar. First is commutative with respect to multiplication. That means the order in which you are multiplying is not important. That means A dot B is same as B dot A. Second is associative property with respect to multiplication. Here also, if you are multiplying three real numbers, then in which order you are multiplying, that is not important. That means either you multiply A and B first and then multiply C to it, or you first multiply B and C and then multiply A to it. Both are same. The next is existence of multiplicative identity. It states that there exists an element which we denote by 1 in our set of real number R, such that if I multiply 1 to any real number A, then I will get my A back. So there exists an element 1 in R such that 1 dot A is equal to A and A dot 1 is also equal to A. But one more important point which you should keep in mind, that this 1 should be distinct from 0. This 1 should not be equal to 0. So this is the existence of multiplicative identity. And next property with respect to multiplication is existence of multiplicative inverse. That means if you have a non-zero element A inside your set of real numbers R, then there exists an element which we denote by A inverse in R, such that A into A inverse is equal to 1 and A inverse into A is also equal to 1. And the last property is distribution property. It states that multiplication distributes over addition. That means if I have three real numbers A, B, C, then A multiplied with B plus C is same as A multiplied with B plus A multiplied with C. Similarly, for post multiplication, B plus C times A is same as B times A plus C times A. So these are the properties of addition and multiplication for real numbers. Now, once we have accepted these properties, which we are calling as algebraic properties of real numbers, based on these properties, we will deduce certain results. Let's see those results. In this theorem, I have listed three results. It states that if Z and A are elements in R such that Z plus A is equal to A, then Z should be equal to 0. It states that no other element will act as additive identity. That means your additive identity is unique inside your set of real numbers R. Second statement says, if U and B are elements in R such that B is non-zero and U dot B is equal to B, then U should be equal to 1. That means no other element can act as multiplicative identity. That means it proves that multiplicative identity is also unique in our set of real numbers R. And third property states that for every A in set of real numbers R, A dot 0 is equal to 0. That means if a real number multiplied to 0, it will be equal to 0. Let's try to prove it one by one. First, we have Z plus A is equal to A in the first statement. Now you consider Z. Z I can write as Z plus 0 because 0 is additive identity. So any element plus 0 is equal to that element only. Now 0 can be written as A plus minus of A because minus of A is additive inverse of A, and by definition of additive inverse, A plus of minus A should be 0. Now I will use the associative property of addition and I will add Z and A together. So this is equal to Z plus A plus minus A. But Z plus A is given to be A. Therefore, I can replace this Z plus A by A and this minus A as it is. So A plus minus A is equal to 0 by definition of additive inverse. And that proves that Z is equal to 0. Second statement, you are given that u dot b is equal to b, where b is non-zero element, and you want to prove that u is equal to 1. So consider u. You can write as u into 1 because 1 is multiplicative identity. Now 1 I can write it as b into b inverse because b inverse is multiplicative inverse of b. So by definition of multiplicative inverse, b into b inverse is 1. Now I will use the associative property of multiplication and I will write it as u times b into b inverse. But u times b is given to be b and b inverse as it is. Now b into b inverse by definition of multiplicative inverse, it should be equal to 1. You have proved u is equal to 1. Third, we want to prove any element multiplied with 0 is equal to 0. For that, you consider a plus a times 0. Then, by using the multiplicative identity property, I can write a as a into 1 and this a dot 0 as it is. Now I will use the distributive property of multiplication over addition and I can write it as a times 1 plus 0. But 1 plus 0 is same as 1 because 0 is additive identity. So this is equal to a dot 1. Now 1 is multiplicative identity. So I can write this a dot 1 as a. So what I have got, a plus a dot 0 is equal to a. That means a dot 0 is additive identity. And we have proved in the first statement that additive identity is unique. Therefore, from your first statement, you can conclude that a dot 0 is equal to 0. So in that way, we have proved all the three statements stated in our theorem. Now here one remark I have written that I have already spoken, that part 1 established that additive identity is unique, that we have already spoken, and part 2 of theorem says that multiplicative identity is unique, that also we have spoken. Now let's see few more properties listed here. It says if a and b are real numbers such that a plus b is equal to 0, then b should be equal to minus a. This statement says that additive inverse of any element is unique. Similarly, in second statement, if you have a non-zero element a and an element b in R such that a dot b is equal to 1, then b is equal to a inverse. In other words, it says multiplicative inverse is also unique of an element. Third is if a dot b is equal to 0, then either a is 0 or b is 0. That means multiplication of two non-zero number can never be 0. If multiplication of two real numbers are 0, then one of them must be equal to 0. Let's try to prove it one by one. First, we want to prove that additive inverse is unique. That means if a plus b is equal to 0, then b is equal to minus a. So we will first observe this fact that a plus minus a is 0 equal to minus a plus a. That is the definition of additive inverse. Now consider b. We want to prove b is equal to minus a. B I can write at b plus 0 because 0 is additive identity. This 0 I can write it as a plus minus a because minus a is additive inverse of a. So a plus minus a is 0. Now I will use associative property of addition to club b and a together. So it will be b plus a added with minus a. But b plus a is given to be 0. So therefore this is 0 plus minus a. But 0 is additive identity. So it is equal to minus a. So you have proved b is equal to minus a if a plus b is equal to 0. That means you have proved additive inverse is unique. Let's see the second statement. A is non-zero. If a is non-zero, there exists a inverse by algebraic properties of real numbers. So you have A into A inverse is equal to 1, which is equal to A inverse into A. That is the definition of inverse. Now we want to prove if A dot B is 1, then B is equal to A inverse. Consider B. B I can write as 1 into B because 1 is multiplicative identity. 1 I can write as A inverse into A, and then it is into B. That is the definition of multiplicative inverse. Now I will use the associative property of multiplication to club A and B. So it is A inverse multiplied with A and B. Now A dot B is given to be 1. So it is A inverse dot 1. But 1 is multiplicative identity. So it is equal to A inverse. So you have proved B is equal to A inverse if A dot B is equal to 1. That means you have proved multiplicative inverse is also unique. Now the third property, that means if A dot B is 0, then either A is 0 or B is 0. To prove this, we will consider first case. Suppose A is 0. If A is 0, there is nothing to prove because you want to prove either A is 0 or B is 0. So if A is equal to 0, you have proved this thing. So there is nothing to prove in that statement. So you assume A is not equal to 0. If A is not equal to 0, then you have to prove B is equal to 0. Let's try to prove it. Since A is not equal to 0, A inverse exists. That means A inverse dot A is equal to 1. Now consider A inverse times A dot B. Use the associative property of multiplication to club A inverse and A. So this is A inverse into A times B. But A inverse into A is 1 by definition of multiplicative inverse, and this B as it is. Now 1 dot B is what? B. Because 1 is multiplicative identity. So you have A inverse times A into B is equal to B. But what you are given A dot B is equal to 0. Therefore, A inverse into A dot B is equal to A inverse dot 0. But we have proved earlier that any real number multiplied with 0 gives you 0. Therefore, A inverse into 0 is equal to 0. So from here you have got A inverse into AB is equal to 0. But here you got A inverse into AB is equal to B. Therefore you can say B is equal to 0. And that proves either A is 0 or B is 0 if A dot B is equal to 0. Now one remark I have written. Part 1 of this theorem established that additive inverse of every real number is unique, that we have already spoken. And part 2 of this theorem says that multiplicative inverse of any non-zero real number is unique. That is also we have already spoken. Now let's see a few more examples. For real numbers A and B, we are asked to prove additive inverse of A is equal to A itself. Okay, that is minus of minus A is equal to A. Then additive inverse of 1 multiplied with A is equal to additive inverse of A. In symbol form, it is minus 1 times A equal to minus A. And the third statement is additive inverse of 1 multiplied with additive inverse of 1 is equal to 1. That means minus 1 into minus 1 is equal to 1. So we will try to prove it one by one. First we will prove minus of minus A is equal to A. That means additive inverse of A is equal to A. Now additive inverse of A is minus A. Therefore, by definition of additive inverse, you have A plus of minus A equal to 0. But what is additive inverse of minus A? Additive inverse of minus A will be that element when added to minus A gives you 0. but that element is A here, and we have proved that additive inverse is unique. Therefore, additive inverse of minus A should be equal to A. That is, minus of minus A should be equal to A, and your first statement is proved. Second, we were asked to prove that minus 1 times A is equal to minus A. Let's see the proof. You consider A plus minus 1 of A. By using the distributive property of multiplication over addition, you can write it as A times 1 plus minus 1. But 1 plus minus 1 is equal to 0 because minus 1 is additive inverse of plus 1. So what you have, A plus minus 1 of A equal to A times 1 plus minus 1, which is same as A times 0. But A times 0 is equal to 0 because we have proved any element multiplied with 0 is equal to 0. So you have A plus minus 1 of A equal to 0. What does it mean? It means that minus 1 into A is additive inverse of A. Because by adding minus 1 into A to A, you are getting 0. That means minus 1 into A is additive inverse of A. But additive inverse is unique and it is denoted by minus A. Therefore, your minus 1 into A should be equal to minus A. Now third, we are asked to prove minus 1 into minus 1 is equal to plus 1. That will follow immediately by using above two properties. Now minus 1 into minus 1. If we use the previous property, it says that minus 1 multiplied with any element is same as additive inverse of that element. That means minus 1 into minus 1 will be additive inverse of minus 1, which is denoted by minus of minus 1. But in the first statement, we have proved minus of minus A is equal to A. Therefore, minus of minus 1 is equal to 1, and that proves the statement which we were required to prove. Let's see the next examples. Here, the first statement says that additive inverse of A plus B is same as additive inverse of A plus additive inverse of B. Let's see the proof of it. Consider A plus B added with minus A plus minus B. Now we can use the commutative property of addition, and I can club A with minus A and I can club B with minus B. So I will have it is equal to A plus minus A plus B plus minus B. But A plus minus A is 0 and B plus minus B is 0. So it is 0 plus 0, and 0 plus 0 is equal to 0. So what you have got, when A plus B is added to minus A plus minus B, you are getting 0. That means minus A plus minus B is additive inverse of A plus B. But since additive inverse is unique, you can say minus of A plus B is equal to minus A plus minus B. Let's see the second statement. It says additive inverse of A multiplied with additive inverse of B is same as multiplication of A and B. That means minus A into minus B is same as A into B. Let's see the proof. Consider minus A into minus B. Now we have earlier proved that minus A can be written as minus 1 into A and minus B can be written as minus 1 into B. Now by using the commutative property of multiplication, you can club this minus 1 and you can write it as minus 1 into minus 1 times A into B. But we have proved that minus 1 into minus 1 is equal to 1. So it is 1 into AB. And since 1 is multiplicative identity, you can say it is equal to AB. So you have proved minus A into minus B is same as A into B. Now the third statement, here we are asked to prove multiplicative inverse of minus A is same as additive inverse of A inverse. That means inverse of minus A is minus of A inverse. Some people denote it in the numerator upon denominator form. So A inverse, which is you denote it by 1 upon A. So it says that minus 1 upon A is same as 1 upon minus A. Let's see the proof. Consider minus of A inverse multiplied with minus of A. Now minus of A inverse, I can write it as minus 1 into A inverse, and minus A I can write it as minus 1 into A. By using the commutative property, I can club this minus 1 with this minus 1. So I will write it as minus 1 into minus 1 times A inverse into A. But minus 1 into minus 1 is 1. And then A inverse A is also 1 by definition of multiplicative inverse. So it is 1 into 1, which is equal to 1. And hence what you have, minus of A inverse is multiplicative inverse of minus A. But multiplicative inverse is unique. Therefore you can say that inverse of minus A is same as minus of A inverse. The next property is, we are asked to prove A into minus B is same as minus A into B is same as minus of AB. So consider A times minus B. Minus B I can write as minus 1 into B. Then minus 1 I can take first by using the commutative property. So I can write it as minus 1 into AB. But minus 1 into AB is same as minus of AB. Similarly, A into minus B can be written as A into minus 1B. Now minus 1 taken first by using the commutative property, it can be written as minus 1 into AB. Now by using the associative property, I can write it as minus 1 into A times B. But minus 1 into A is minus A. So it is minus A into B. So you have proved A into minus B is same as minus A into B, and it is also same as minus of AB. So that statement is proved.